Thank you. Good evening. Welcome to the Barbados Association of Professional Engineers monthly technical webinar for December 2025. My name is Vincent Jones, your moderator for this session. This is a CPD, that is a continuous professional development event, and carries a value of 2 CPD points. Please contact our secretariat to have your CPD information forwarded to you should you wish to claim those points. A bit of housekeeping for this evening. Please note that these sessions are run as follows. We will introduce our presenter, who will present for between 30 and 40 minutes. We then open the session to our general audience to ask questions and interact with our guests. This is done either by raising your hand, at which time the moderator, that's myself, will acknowledge you and invite you to ask your question. Alternatively, you can post your question in the chat, and I will ask the question on your behalf. We ask that you please mute your electronic device until your asked question. Tonight's topic is reducing the vulnerability of masonry houses in the Caribbean to earthquake and hurricanes, and is being presented by engineering fellow Dr. Grenville Phillips II. Before we get on to Grenville, I just want to give you a couple of notices. On Friday, December 5th, 2025, this Friday, you are invited to the BAPE line, and this is being held at the LV Harcourt Lewis Training Center, which is at the Barbados Public Workers Cooperative Credit Union Limited headquarters, located at the Keithbourne Complex, Belmont, St. Michael. That event takes place from 5:30 until 9:30 this coming Friday. So if you are a member or a friend of the association, you are invited to attend. I also want to remind you that with the change of year, January 2026, your yearly membership fees will become due. Just a reminder for our members, the corporate fees are $300 for the year. The affiliate fees are $225.25 for the year. Graduates, $150 for the year. Student members pay $20 for the year. Those of you who are professional engineers, your registration fee is $1,250, and that must be paid in to the registry at the Supreme Court before the end of January. So make sure when you're budgeting for your Christmas festivities that you remember that you have some fees to pay come January. Without further ado, we are going to get ready to move to our presentation for this evening. Engineer Grenville, are you ready to present, sir?
Yes, sir, I am.
All right. So, engineering fellow Grenville Phillips is the consummate engineering professional who has, and I'll let him do an introduction of himself, but who has recently completed his doctorate in engineering studies, and he will speak a bit about what he would have studied and tell us a bit about that journey for him. Now, Grenville is not just an engineer, but he also makes himself available to regional bodies to go and do risk assessments, etc., after disasters in various disaster-prone areas. So he will probably tell you a little bit about that and the work he has done. He doesn't get up there and wave a flag, but it is very critical and important work that needs to be done after we have these natural disasters in the region. So without further ado, Grenville, I'm going to let you take the podium, sir.
Thank you. I'll share my screen. Share. And get it. Okay. I'm assuming that you can see my screen. Someone could just say yes.
We can, yeah,
And you
no,
can see my cursor as well.
I can see your cursor, but we have
Very
some
good.
gray areas on your first page, Grenville.
First, there's only one page here.
And I got some,
Oh, let me see if I minimize this. Okay. Um, is this better?
yes, it is.
Okay. Yeah, so my name is Grenville Phillips. I got my doctorate in 2022. I'm the current president of Walbrent College, and I'm going to present on reducing the vulnerability of masonry houses in the Caribbean to earthquakes and hurricanes. Uh, right, so people are waiting. I'm not sure if you see this here. People waiting in the room. I'm not sure if you see that as well.
We
That
have
comes
that
up on
sorted,
my.
Grenville. You just go ahead and do your thing. We're dealing
Okay,
with the back stuff.
very good. Yeah, so I gave this another sub um, title, Verifying Design Assumptions. And what I'm going to do is go through my doctoral studies and uh, the benefits then to the profession from that. So I decided to give an opinion on the progression of knowledge. When I did my bachelor degree, my understanding after looking at the books that it was textbooks and after graduation, I decided that all knowledge in this area is already known. And my role is to be a cog in the wheel, basically to take what is known, already known, and apply it. So the cog that maybe that's me there, and all the rest of us, just engineers, just sitting down and doing work. Um, and then when I got to the masters, when I was doing my masters, I understood that there are gaps of knowledge. There are gaps in my knowledge of what is known. And my role then was to fill those gaps to increase my productivity in applying that knowledge that was already known. Then after working for a while, then at the doctoral level, I recognize that there are knowledge gaps in the profession itself. And my role then was to fill those gaps by making an original contribution to professional practice. And that's what a doctorate in engineering is all about. If you don't make an original contribution, then you don't get the doctorate. They will give you a Master of Philosophy, an MPhil. But if you reach that level, then you get your doctorate. So what I'm doing here, in addition to showing you what I did, is to encourage those of you who have your bachelor to pursue your masters, and those who have your masters to pursue a doctorate. It is not that difficult um, once you've finished your masters and you've gotten some work under your belt. This is the Caribbean, and essentially this was my laboratory for the doctorate. So when you're doing a doctorate, first thing you have to do is define the problem that you're trying to solve. So the problem definition, building damage from hurricanes and earthquakes is normally blamed on substandard designs, substandard construction materials, and substandard construction methods. What is normally overlooked in the Caribbean are assessments of design assumptions that are used to develop the building standards that guide engineers. It is this issue that this research plans to address. So, over the past 30 years, there have been several hurricanes and major earthquakes that have impacted masonry walls, houses in the Caribbean, and there is now sufficient data to identify critical design assumptions that may have inadvertently resulted in significantly under-designed buildings. And then you have to identify the aim. What is it you're trying to do at the end of all of this? And my aim was to propose design recommendations to reduce the structural vulnerability of masonry houses in the Caribbean to damage from hurricanes and earthquakes. And you must know there's a lot of advice given in the codes. So this was my aim. Then you have to explain what method you plan to use to achieve that aim. So critical design assumptions were identified during damage assessments following recent extreme events. And they are the basis of the 4 research projects that comprise this thesis. And I've started doing damage assessments from hurricanes in 2004. And the last two are in italics because this happened after the doctorate, but um, those are the ones that I assessed. So it's quite a body of um, evidence that I can use for the doctoral program. Then, since you're doing a set of research papers, essentially, they have to tell a story. So you then develop some story. Um, why? Why question design assumptions? So the typically observed wind damage was to roof cladding and its supporting timber frame. However, there were instances of cladding failures where significantly more than the number of screws required by the building standard were used to connect the cladding to the timber frame. And here's the example. So this is a school. It still had the ceiling in under the gable end, but screws at 3-inch centers. So more than that is required. So such evidence suggests that in addition to examining construction errors and structural engineering design errors, the assumptions used to determine the structural design of the cladding and timber frames should also be examined. Since persons normally build what they can afford, the assumption that building a house to survive a Category 5 hurricane is generally unaffordable to homeowners should also be investigated. So I'm sort of telling the story of why I'm looking at cladding and looking at timber frames and also looking at affordability. The typically observed earthquake damage in Haiti was to unreinforced masonry walls. The type of masonry constructed was generally unreinforced confined masonry. Given that both confined and reinforced masonry are used in the Caribbean, and that confined unreinforced masonry is being promoted as the superior masonry solution to seismic loads, both methods' response to seismic loads should be examined. So this is Haiti, where walls collapsed, they were unreinforced. And here, collapsed unreinforced masonry walls, they did have these column stiffeners, but still the walls collapsed. So the design assumptions that I came up with is hurricane wind loads can be applied statically. That's a design assumption in our codes. The second one is that hurricane wind loads are of short duration. That's what's stated in our codes. The third is that the construction cost of timber frame roofs to survive known Category 5 hurricanes is unaffordable for most homeowners. And that is just almost common knowledge when I was doing the doctorate. And 4, confined masonry performs better than reinforced masonry under seismic loads, and that's what was in their codes. So to test the assumptions, the research was divided into 4 work packages, which are the thesis's research projects. So I'll go through them then. This is research project 1, dynamic wind loads on roof cladding. That's the title of it. And then you list the design assumption. Dynamic loads on cladding can be applied statically by applying an increased factor. Let me just come out of this and just show you what I mean. Stop sharing. Right, so you can see me. The understanding is that a wind load is applied as a wind pressure against a wall. To deal with the dynamic wind loads, No, dynamic wind loads are usually they're gusts, going, but that dynamic um, load is applied statically by applying a factor to your load, and it's usually a factor of two. Still applied statically, not dynamically, applied statically. So there's basically a doubling of the load. So let me share again. Yes. So there's typical damage right, from windstorms. The typical damage is cladding loss and also the frames. But usually the cladding goes, and if the cladding is well connected to the frame, then the cladding and frame go. And these are the types of cladding that we usually have in the Caribbean, the trapezoidal type, where it's preferred to fix screws to the purlins or the frame in the valleys, and you have the crest. Similarly, crests and valleys in the sinusoidal type. So the method, damage predicted from an equivalent static application of loads, and this came from wind tunnel tests described in the American Society of Civil Engineers, ASCE 716, that basically came out, was done in 2016, was compared with actual damage from Category 5 hurricanes. So we're comparing the predicted from the code to the actual from an actual event. The predicted damage was to the high pressure end zones of the roof and to the cladding. And then possible explanations for failures that were significantly above those predicted were identified and assessed for their likelihood. Yes. So looking at the high pressure zones then, high pressure end zones. This is a gable-shaped roof. And according to AC 7, we have an interior area which attracts some high wind pressures. And then we have the ridge and the eave and the gable end. These attract higher wind pressures. And then we have these areas in black that attract the highest wind pressures. And to identify the dimensions of these areas is A. And once the width is less than 9 meters, A is 0.9 meters. So we know what the areas of high pressure are. And therefore you attach more fixings, more screws to those areas. And for the frame now, for the frame, the timber frame, the area is 2A. That's the area of higher wind pressure, 2A. And in a shape roof, again, 2A, that's the area where the higher wind pressures are. So these figures show a 2A dimension width of a high pressure end zone of the building. The least horizontal dimension of most houses in the Caribbean is rarely more than 9 meters. Therefore, most houses will attract an A value of 0.9 meters, resulting in a minimum end zone width of 1.8 meters. So the observations is that the general pattern of vulnerable roof areas from wind tunnel tests was found to be similar to the pattern of damage observed from actual Category 5 hurricanes in the field. However, even though the general pattern was similar, the extent of the observed damage was generally greater than that predicted by ASCE 716 for cladding. So the pattern of damage is similar, but the extent, 2.4 meters, not 0.9. Um, Marsh Harbor, this is in Bahamas from Dorian. Again, the pattern is similar, but the extent is greater, 2.4 meters. Pattern similar, extent greater. Pattern similar, extent greater. That's generally how it was. The pattern was similar, but the extent of damage was greater. Um, Now, in addition to this, now there's a lot more evidence from the recent hurricanes that we're still analyzing. But looking at the percent accuracy for the structure, all right, 100%, 75%, 60%, 150%, 51, 51. So that's on the structure, but it's really the cladding that I was looking at. And on the cladding, 37.5, 50%, 30, 25. So it's basically failing mostly in the cladding. One was 100. So looking at the percent damage versus the height and versus the width and versus the length, try and come up with a better predictor. This one seems to be the better predictor, where we're looking at the length. This is the height, width, and the length, and you want something with a lower spread. So that will give you a bit more confidence. And looking at it, we see that lower standard deviation for the length and lower spread for the length, and therefore selecting the length and using 20%, which is the mean value, that seemed to be a better predictor. So the recommendations were the current method of determining the extent of the high pressure end zone in rectangular buildings is to define this end zone distance as a function of the smallest horizontal dimension or distance, sorry, this is the width, and the length and the height. So a new parameter and end value was proposed for identifying the likely extent of the vulnerable roof area for hurricanes, namely 20% of the building's longest horizontal dimension for a single-story building. And that was it. So that was the original contribution to that part of it. And again, that's only one part of this project. The main one now was the cladding. It was a case study done in Anguilla under Hurricane Irma when the Barbados was there and observed four failure modes. One, the metal cladding tore and pulled over the screws. So it tore, and this metal cladding pulled over the screw that was there. The second type was that the cladding ruptured, it ruptured along this edge and tore near the screw. And I've seen this generally wherever we go and look at hurricane damage. You usually see this pattern on the cladding connected to the purling. So there's the rough, tensile, ruptured edge, and there's the smooth, sheared edge. Is it there? Rough, 14 millimeters on this one, and had a few samples. And then the third mode of failure was that the screws pulled out of the supporting timber purlins. There's a screw there, but it pulled out of the timber purlin. But it didn't tear the cladding. And then the fourth method of failure was that the cladding stitching screws pulled out of the supporting metals cladding. This is the one that was below, and there was a one above, and it tore out of this. And since the evidence was there, I was able to identify all the locations, all the failure locations. According to the code, the predicted damage was the gable ends and corners, the gable ends and corners here, the gable ends and the corners at the ridge and the corner at the E. That was where the damage was supposed to be using the design. And there was supposed to be no rupturing at all. But the observed actual damage from the actual event was that the sections of roof failure was all over the roof. And not 11.8, but 80% of the roof. And not 0, but 5%, and 20%, and 40%. So then you come up with the explanation. What's a normal explanation for this then would be that unexpected cladding failures can normally be explained by weakened component materials and underestimated applied loads. So the materials, however, were observed to be in fair condition. Even the screws, they were not badly corroded. They were in good condition. Or fair condition, I would say. They were not new screws. So dynamic loads are determined then in cubic by you have a static parameter. Here's the pressure and two coefficients, exposure and shape. And then that's multiplied by a dynamic parameter, 2 for the cladding, sorry, 2 for the structure and 2.5 for the cladding. And that's how we get our dynamic load. So you basically double it for the structure and increase it by 150% for the cladding. And that seems reasonable. AC 10, you had the pressure static parameter, but then the difference in gust effect factor and external and internal pressure coefficients tends to be less than 2 for the interior and greater than 2 for the remainder. So you multiply that by a gust effect factor. And then in AC 716, same thing, but they introduced a elevation factor. And that elevation factor reduced with height. So the higher you go, the less pressure. So the static wind speeds required to overcome the load resistance of interior screws. So calculating then what the wind speeds would have to be, what the wind speeds would have to be to overcome the four modes of failure, 625 kilometers per hour, 1,683 kilometers per hour, 383 kilometers per hour, and 783 kilometers per hour. And these are significantly greater than the 376 kilometers per hour from Hurricane Allen in 1980, which was the greatest one that we had. So we certainly didn't underestimate the load, but clearly it could not have been just the wind because we didn't have these gusts. So the analysis then, the static application of the wind loads could not explain the observed damage. The damage can be explained by the dynamic response of the building's material to dynamic wind loads. So it could be explained by the dynamic response of the building's materials to the dynamic wind loads. So the effect of dynamic wind loads, the cladding is deformed and it pulls over the screw. And the cladding ruptures and tears. And the screw is gradually pulled out of the supporting timber. And I'll show you examples of this. So if we space the screws 1 foot apart, 300 millimeters apart, and these ridges are 6 inches apart, then during the suction forces, this rises. Then it falls and rises and falls. It flutters. It flutters, and as it flutters, this being the deflected shape, then there's increased stress at the screw hole. Increased stress at this hole, and that then explains why you will get that tearing and the pulling over, and why you will get this rupturing and tearing. Not by the static application, but not the static application of the load, but the dynamic response of the material. And here now, if you put a screw in the middle, but not tighten it, then there will be fluttering, and the fluttering causes this to keep knocking it out. And it keeps knocking it out until it's gone. It's knocked out completely. Once you have that play, once you have space for play to occur, for movement to occur. And therefore that explains the loss of the screw. And once the screw is gone, then increased stress on this nail, near this nail, now this screw, and we get the two from the previous one. And this is an example of it observed in category 4 Hurricane Beryl, where like this one in the middle is knocking out, and there's a nail actually, but between these two, which are fixed in place, this one is gradually coming out. These two are fixed in place, and the two are coming out. So you can appreciate you don't want to have flutter at all. Once you have this fluttering, then it's going to keep hammering the nail out. And this is the screw where it's hammering it out, the screw, and you have a little dimple, a little dent in the sinusoidal cladding. Again, on its barrel. So the original contribution to professional practice then is proposing a new design approach. First, design the joints to satisfy the equivalent static loading requirements of the building standard. You must comply with the building standard. You must comply with the design standard. That in some cases is a legal requirement. But if you don't, then if something happened, then someone's going to ask you the question, well, did you comply with the code? You must be able to say yes. So first advice is comply with the code. But after you have complied with the code, then number two, assess and address the vulnerability of the joints to accelerated cladding movement from dynamic loading. So then the cladding should be restrained where possible to reduce any play and the risk of the cladding's acceleration through that play. And the areas where progressive failures are likely to commence should be identified and strengthened. So this is a result of that. So even though, according to the code, in the interior, you can put a screw at 1 foot apart or 300 millimeters apart, because of the dynamic behavior of the material, the response of the material, and therefore the loss of the screws and the increased stress around the screw at the cladding, every valley should be, the connection should be in every valley. And the screws are not expensive, so this should not cost that much. At the gable ends, eave, ridges, hips, and valleys, where the pressures are higher, then you space them at 75 millimeter centers for a category 5 hurricane, 75 millimeter centers. Now, I went looking and I found generally, especially when you go further away from the, I guess, the epicenter, if you will, or where um, the storm made landfall, then you start to see where the vulnerable areas were or are. And again, it's generally the stitch and screws. There's movement at the stitch and screws, and the failure starts there, and then when one is gone, then the rest go. So you want to stop it at the stitch and screws, the vulnerable location. And therefore, at the stitch and screws, you put screws on either end. But again, if you put a screw on either end, then you have a long distance here, creating fluttering. So you put one at this end as well, the same way that you did in 3-inch spacings. And that then should secure that stitch and screw vulnerable location. So the research project number 2 then, wind load durations on roof timber frames. The design assumption is that wind load durations on timber frames or timber members is short term. So another typical windstorm failure is the timber frames that support the roof cladding. Timber can resist significantly greater than its reference maximum load when those loads are applied for short durations. It's a really wonderful quality of timber, where the shorter the load, you can increase the reference strength to accommodate those shorter duration loads. So building codes assume that the wind loads are short duration events. So timber design strengths are artificially increased. And is that assumption that was investigated. So again, this is important because the reference resistance of timber is increased by multiplying it by a load duration factor if the load duration is short. So if it's a permanent load, multiply it by 0.9. But if it's 10 years, then it's the reference strength that they determined in the lab by loading the timber. And that's usually for live load. You apply a load duration factor of 1. But if it's a 2 months load, and they tell you that's snow, then you increase it by 15%, 1.15. And if it's a 7-day load, and the example that the code gives is construction, a construction load during construction, then you increase it by a quarter. You can increase the timber strength by 1.25. But if it's wind or earthquake, then you increase it by 1.6. There's a significant increase. And if it's an impact load, you can double it. You could double the reference strength. So rather than getting exceptionally large size timber, if it's an impact load, no need to do that. Just double the reference strength. And again, that's a wonderful um, uh, aspect of timber. So curves were done so you can identify these things. So that is normal, 10 years. That's wind and earthquake combined, 1.6. So the International Code Council, the International Building Code references the American Wood Council, and they state the 10-minute load duration factor, because we're looking at wood, the 10-minute load duration factor is conservatively estimated as the adjustment for the cumulative effect of these two, wind and earthquake, load conditions. So they're quite confident that it conservatively estimates those two. So the load duration modification factors, so there are modification factors in the American Wood Council, in the International Code, in the ICC, it's um, but yes, load duration factor, it's CD, but this one is LMF. Same thing, 10 minutes for wind and earthquake. So I guess they got it from the American Wood Council. So the method was to determine the durations of both tropical storms and hurricanes that impacted the Caribbean for 50 years, typically the building's design life. Compare the cumulative storm durations with the wind load durations recommended in timber design standards. So use these tracking charts. That's the one 2017 where you had Irma and Maria. So essentially from those, you get the storm's direction and speed. You get the direction and the speed. And you also get the diameter and of the hurricanes and the tropical storms from the National Hurricane Center's reports. So knowing where it was and the direction that it was and the speed that it was, and this is the island, then you know the duration because you know the distance, and the distance divided by the speed will give you the duration. So doing that for tropical storms from 1970 to 2019 for all Caribbean countries, and therefore you can get the number of storms, the impact hours of those storms, and therefore the impact days, with a day being a 24-hour period. And doing that for hurricanes as well, for all Caribbean countries. So the observations and analysis, of 277 tropical storms and 163 hurricane impacts in the Caribbean between 1970 and 2019 showed that there were not short duration events. Therefore, the artificial increase in design strength resistance based on the assumption that the wind loads were short duration events was not justified in the Caribbean. So the Storm duration, tropical storm 20 days, and the hurricane between 0.2 and 5.7 days, depending on the island, with a mean of 4.9. So 10 minutes wasn't cutting it. So it's more like 7 days for a hurricane. So the recommended wind load duration factors for the American National Design Specification of Woods Construction, which is the typical one that you use then with ASE 7, or the Eurocode 5, Design of Timber Structures, or the Canadian Standards Association, Engineered Design in Wood, or Cubic 1985, Structural Timber, instead of 1.6, if you're using a tropical storm, 1.15, or if you're using a hurricane, 1.25. You should be using 1.25, and that should be in our Caribbean application documents in the Caribbean. And the Eurocode gives you 1.1 or 0.9, should be 0.8 if you're using tropical storms, or 0.9 for hurricanes. The Canadians, well, 1.15, that's correct. But tropical storms 1, and cubic, not 1.33, but for hurricanes 1.25. So you don't artificially increase it by 33%, but by 25%. If you're using the methods in cubic. So the original contribution to professional practice is that more appropriate low duration coefficient values for the Caribbean were recommended in timber design standards designed to guide designers. Then research project 3, the affordability of category 5 hurricane resistant house roofs. The assumption made was that the cost to build a roof to survive category 5 hurricane winds is unaffordable to most homeowners. So we investigated that assumption. That's a typical roof on a masonry house, rafters, purlins, and the roof cladding. So the method was to select 3 common house roof areas with hip and gable shaped roofs of varying roof slopes, 0 to 45 degrees. Design the roof to resist both category 2 and category 5 hurricanes. Category 5 being 225 miles per hour, 3-second gust hurricane force winds. Calculated the amount of construction materials required to construct different roof shapes and spans. And again, the reason why I went to 2 and that level of 5 is to really produce the most conservative result. And assess the damage risk by determining the frequency of windstorm impacts in Caribbean states over the past 50 years. Now, this I've updated because it is significant, and I'm doing some postdoctoral research trying to find out why this happened, and I believe I found out why. So before 2000, we tended to have 8 category 5 hurricanes in the Caribbean every 30 years. So there were 8 between 1910 and 1939. There were 8 between 1940 and 1969, that 30-year period. There were 8 between 1970 and 1999, that most recent 30-year period. But then suddenly after 2000, we had 8 in 5 years, not 30, 8 in 5 years. And then there was 6 in 4 years. And we were monitoring this little cluster that was developing. But right now, after Melissa, there's 7 in 4 years. Something is happening with our weather system. There is, the climate has changed, definitely. This is incontrovertible proof. The climate has changed. The only thing is, who is changing it? Well, it seems to be changed by humans. It's man-made climate change, I believe. But which men? Who are these men that are changing this climate? Who are these men? And I think we identify them. Well, we possibly can. But that's a research paper. But clearly, it's changing. And this is now the pattern And therefore, if you're designing to hurricanes, you better design to Category 5 level hurricanes. You better. To design to anything less is knowing what we now know um, is not good. It's not good. So we should design our buildings to Category 5 hurricanes. And again, this is the year 2000 when things change. And I guess well let you know what changed was there was a lot of development, sorry, um, in cloud seeding, trying to improve the weather for
Hi,
some.
Chris.
Hello? Yes. Well, when I have 5 minutes left, let me know and I'll run through them quick. Right, so I'll come back to that then. Um, Comparative summary. So calculated the costs and found out that the difference in cost, you basically are doubling the material cost of the roof. That's the additional material cost of the roof. So you're basically doubling it to get to a category 5. And looking at a cost per square foot of $200 a square foot, Barbados dollars, you end up with about 5%. 5%. And again, you're looking at a gable roof for a 600 square foot, 800 square foot, 1,000 square foot house, various roof shapes, and hip roof, same thing, and 5%. And that was for the small one. And the larger house you get, it goes down to 4, 4.5, basically. So the benefits of building a larger house there. Observations and analysis. The additional cost of construction materials for a roof to survive a Category 5 hurricane over Category 2 was within the normal contingency amount for a house building project. And the risks of being impacted by tropical storms and hurricanes several times during the 50-year design life of a house was likely because we looked at the frequency and basically an average of 11 and a half years. So the roof may require replacement between 4 or 5 times during a 50-year design life, on average in the Caribbean. The original contribution to professional practice is that houses in the Caribbean should be designed to resist winds from recent Category 5 hurricanes that impacted the Caribbean, since it is shown to be affordable to do so. So if it was not affordable to build a roof to Category 5 hurricane, then don't do it. But since it is affordable to do so, and it is, as I said, 5%, but the larger the house, and therefore the larger the building, it is even less than that. The research project number 4, seismic loads on confined and reinforced masonry walls. The design assumption is that confined masonry is the superior masonry solution to concrete masonry blocks. So this is important because since the Haiti earthquake in 2010, where 300,000 people reportedly died, confined masonry has been actively promoted in Haiti and around the world as the better masonry solution for earthquake resistance. There are benefits to the Caribbean region if this assumption is found to be true, or safety risks if it is found not to be true. So this is reinforced masonry. You reinforce vertically and horizontally your walls, and therefore you have in-plane loading and out-of-plane loading that the reinforced masonry can resist. But confined masonry, you have these belt columns and beams that confine unreinforced masonry elements. So there's reinforced masonry before grouting has taken place, where you reinforce your block cores. And there's confined masonry, where this here is not reinforced. These are not reinforced at all. They're unreinforced, but you have these belt beams and columns. They're not designed to withstand, movement. They're just there to confine your unreinforced masonry. So they're not designed as normal columns. So method, design a modern masonry single-story starter house and design the walls to four building standards, calculated the cost of the wall building materials required for each seismic design, and assessed the risks of construction errors by identifying typical non-compliant house building practices. So that's the house there. Open concept, 3 bedroom, 2 bathroom, and a pantry, 1,000 square feet. Comfortable. And these are like 12 by 12. Using cubic compliant vertical rebar layout. So usually the spacing is 800 millimeters. However, sometimes it's 600 or 400, depends on where the doors and windows are located. So you can't just say 800 and calculate it that way. You have to draw out every bar so that you can get the actual number of bars and the ties. And the Haiti Building Code, the most recent one, they space the rebar at 400 millimeter spacing and grout the entire 2 meter shear wall. And the Masonry Society, which is the one adopted by ASE 7, they have rebar in the joints. And confined masonry network, so you have these belt columns and beams. Is the column there's both directions. So the summary cost of the masonry methods. Actually, so the confined, I put this one here for comparative purposes, but really you are not supposed to be using 6-inch or 150 millimeter wide walls for confined masonry. So really is this, but I decided to just check it. But again, it's the most expensive one of all of them. So reinforced masonry was found to be the stronger, less expensive, and more durable masonry solution for concrete blocks than confined masonry in the Caribbean. I'd like to just briefly note the role of the Earthquake Engineering Research Institute. It's relevant to note the role of this institute in the recent promotion of confined masonry in developing countries. The objective of the institute, taken from their bylaws, is to reduce earthquake risk by advancing the science and practice of earthquake engineering, by improving understanding of the impact of earthquakes on the physical, social, economic, political, and cultural environment, and by advocating comprehensive and realistic measures for reducing the harmful effect of earthquakes. Article 1 is wonderful, wonderful. In 2008, they established the Confined Masonry Network to promote confined masonry construction in seismically prone areas of the world. Before the 2010 earthquake, confined masonry was a common residential construction method in Haiti. Following the earthquake, confined masonry was actively promoted as the only masonry solution for Haiti. And I was there over 12 times between 2010 and 2016 and could not get them to accept reinforced masonry. The only thing they would accept is confined masonry. And I couldn't understand why. The international trainers recommended, and there was training Haitians as well, but others were training them as well, but they recommended that only confined masonry should be taught to avoid confusing, among others, the workers, the population, other organizations, and the government. They actually passed an edict while I was there, when they realized that I would be training Haitians, forbidding anyone but that group from training Haitians. And to their credit, the organization that brought me there said, look, we brought you and you train how you want to. And therefore, I did not comply with that edict. But you had a couple of engineers that came down from Arup in the UK. And they were so intimidated that they spent their time there not training anyone. On the 21st of September 2018, the Earthquake Engineering Research Institute issued a policy statement while I was doing my research into this that included the following: international building code writing bodies, academic institutions, and international aid agencies should promote the use of confined masonry as an affordable, which is not, earthquake resistant construction choice for emerging economies in seismically active regions around the world. So they're not going to developing countries, developed countries, because their codes don't have confined masonry. They wouldn't put it in. But here we have um, targeting the emerging economies. Confined masonry is a technology that, if built correctly, performs well in earthquakes. Well-constructed confined masonry buildings have been observed to incur little or no damage when exposed to strong earthquake shaking. And again, you can make that because you keep saying well-constructed, and very few are. I could not find a single well-constructed confined masonry after 2010 Haiti, despite them being supervised by persons outside of the region. In contrast, again, this is the Earthquake Engineering Research Institute while I'm doing my research into reinforced masonry and confined masonry, comparing them. In contrast, the more commonly used systems, like reinforced masonry, have proven to perform poorly in earthquakes as typically constructed. That is not true. Agencies and international NGOs involved in post-disaster reconstruction work should include training sessions for local masons in the design or construction of confined masonry as integral components to their programs in seismically active areas. And they pursue that with zeal. Again, reinforced masonry addresses both in-plane and out-of-plane loading. Unreinforced masonry does not address the out-of-plane loading, and that is how the failures tend to occur. Not plane, in plane is okay, it's the out-of-plane. Is the earthquake shaking in this direction? That's the problem with confined masonry. While I was doing my thesis, on the 14th of August 2021, Haiti was struck by a magnitude 7.2 earthquake. Approximately 2,248 people joined the approximately 300,000 that had died 11 years before. 12,783 were injured. 53,853 houses were destroyed. Confined masonry, I might add. 83,770 houses were damaged. The damage occurred in the same area, in the same areas where the 2010 earthquake struck, and they rebuilt them using confined masonry. Those were unnecessary deaths. A preliminary damage assessment report was prepared by the United States' National Science Foundation's funded Structural Extreme Events Reconnaissance, called STEER, is that STEER team. The STEER report identified 4 building types in the affected areas: unreinforced masonry, reinforced masonry, so that's probably some of my students, confined masonry, and masonry infilled reinforced concrete frames. So the typical reinforced concrete frames that were designed and then masonry infilled. It reported that most of the damaged houses were of poor quality confined masonry that performed no more reliably than unreinforced masonry. And unreinforced masonry buildings are not expected to survive earthquakes. That's page 24 of their report. Despite the tragic evidence of damage to confined masonry buildings, the STEER report made the following recommendation. Confined masonry has been promoted in Haiti and other low and middle income countries with high seismic risk as a viable typology for residential construction. Well, yes, it's been promoted by the Confined Masonry Institute. Unfortunately, this typology has yet to be formalized in many international building codes and standards, though important steps have been taken in this direction by a number of countries. The ability to validate the performance of this construction style in this event, and particularly performance when variable levels of confinement are achieved in highly resource constrained environments, can press on with the necessary evidence to promote this system globally. I mean, it's like one person identified the damage and then it was passed on to the confined masonry network or someone to just write this madness. As well, confined masonry is equally effective in resisting tensioning and autoplane failures in masonry walls under hurricane uplift pressures, the promotion of feasible earthquake-resistant implementations of confined masonries in lower and middle income countries in the Caribbean will be advantageous for advancing multi-hazard resilience. So you just throw in those phrases and hope that someone just reads um, the recommendations and adopts this. Interestingly, the STAIR report did not comment on the performance of reinforced masonry buildings and did not include reinforced masonry as a recommended housing solution. This ignored it completely. So the original contribution to professional practice, reinforced masonry is a better masonry solution for concrete blocks in the Caribbean. Confined masonry is a suitable masonry solution for walls built of stones and solid bricks because they don't have cores in them that can receive reinforcing bars. And therefore, the better method for those concrete blocks with cores is reinforced masonry. But where there are no cores, confined masonry is suitable. So I came up with three policy recommendations. One residential building standard should be developed for the entire Caribbean to the same magnitude of wind and seismic loads. The wind standard should be a 200 mile per hour, 3-second gust. And masonry houses should be designed to survive both in-plane and out-of-plane loads from this magnitude 7 earthquake that impacted Haiti in 2010. And that's it. And after going through the research, then I was awarded the doctorate. I could let you know then that after this, I tendered on a job, the college did, and wanted to design a regional building code for houses in the Caribbean. And we completed that and also did a learner's guide, which is a user-friendly version of that standard, which has been accepted by CARICOM as a Caribbean standard. And it is the 225 mile per hour gusts. Right? Willing to entertain any questions?
Hello, Grenville. Thank you so much for your intriguing and very instructive presentation this evening. I think all of the members here, certainly those with a bent towards civil and structural engineering, would have been exposed to some information backed up by credible research and data that is indeed food for thought. I would like to open up at this point in time the session for questions. And I see Peter Thompson right off the bat has his hand up. So Peter, I'll let you go first.
You're muted, I think.
Peter, check and see if you're muted. You can proceed with your question. Okay, we'll come back to Peter. Jerome Garwood, proceed with your question, please.
Yes, good evening.
David.
Thank you for the presentation. Very informative. One thing that stood out to me was the position that the EERI continued to took despite the evidence, despite sufficient evidence that confined masonry wall cannot withstand the earthquake that that the Caribbean is facing. So it's really mind-boggling to me, especially given the amount of deaths and as the presenter said, unnecessary deaths. So I just wondering if you could shed some more light on that as to why they are so vigorously defending confined masonry wall.
Yes, I have some thoughts. When I was deployed there, 2010, I for the next year or so, I could not understand why this was being pushed. And then I wrote an article in the Institutional Structural Engineers Journal. And there was a lot of pushback then from the Confined Masonry Institute. And the institution asked me and them if we can get together and just come up with a combined position. Let us just share data and then work and come up with one combined article for the benefit of all engineers. And I tried my best. I tried my best, but they were not willing to give an inch. And the general position was, look, I have a PhD, and therefore you should listen to me. That's basically it. Right? That's basically how the arguments went. I have a doctorate, I have a PhD, and therefore I'm authority in this area, and you natives should listen to me. And it didn't work out. So they wrote their article, and I wrote my article. We wrote two separate articles. But they wrote theirs, and then I wrote sort of explaining where I thought they were just terribly out. And it's then that I thought, well, I'm going to try and get a doctorate somehow. But then I never thought I couldn't see any opportunity to get one, and I wasn't willing to leave the profession to go and study to do a doctorate. I just didn't have that time. But then doing a doctorate in engineering, that opened up, and I was able to do it in Barbados or in the Caribbean, really, with the Caribbean being my lab. I just went up to England once a year for a couple of weeks to do small courses, but generally I was in the Caribbean doing the work. So why it is, I really don't know. I think the only explanation that makes sense is that someone wants Haiti to remain vulnerable to earthquakes and hurricanes. I could not find any 24 gauge, 26 gauge, 28 gauge roof cladding because I said I had a number of deployments there. Well, a couple of them rebuilding schools and trying to find materials, going to all the hardware stores, and they cannot find anything of any value. We had to basically double up the cladding, double it up to try and prevent it from tearing. This thing is so weak. People used to take it and roll it up and put it under their arm and drive on their motorcycles. That's so you can't bend, proper cladding like that. So I just think that someone wants to keep Haiti vulnerable. And there may be
Okay.
reasons for that, and I don't think I should share those here.
A follow-up
But I'm
question,
concerned.
Follow-up question, Dr. Phillips. First a comment, I agree. It it seemed that someone is sabotaging the life of Asians. I know you presented that what was it? It's a section of a presentation where you prove that, think it was improving the quality of our roofing is affordable. But
Yes.
I think you're talking about the Caribbean generally. So
Yes.
is it affordable in Haiti's economy to start using reinforced masonry wall? Is it affordable? Were you able to prove that as well? Or maybe I missed it in your presentation.
Yes. Yes. Wherever you are in the Caribbean, reinforced masonry is
It's
cheaper.
affordable. Okay. Well,
Yeah. Well, when I say affordable, yeah, reinforced masonry, yes, is affordable. Yeah, definitely, because it's cheaper than confined masonry, which is what they're doing now. It's cheaper than what they're doing now. So if they could afford to build now, you use less steel using reinforced masonry. You use less steel than confined masonry, where you use more steel. Yes, you're not reinforcing the blocks. What you are is you're building these reinforced concrete. Um, not they're not really designed as columns, but you can call them basically stiffeners, column stiffeners, and belt beams to confine these unreinforced blocks. So all that with all the links that you're putting in, a lot more expensive. Well, it is more expensive, I should say, not a lot more. It is more expensive.
All right, thank you for that, Jerome. And I do want to acknowledge that we do have colleagues joining us this evening from across the region. We have colleagues from Trinidad and Jamaica, including students who are currently enrolled in the civil engineering program at St. Augustine. So I just want to extend the welcome to you this evening. Peter, are you ready to ask your question now?
Yes, how you doing, sir? Good evening. Good evening, all. Sorry about
Yes.
earlier. I was having some technological challenges getting to unmute. Excellent presentation, Grenville, as usual. I have two questions for you. One relates to the cladding.
Yes.
Based on the failure that we have seen with the cladding, I know that you've indicated that stitching screws at 75 millimeter the lengths will
No,
be
no,
able to
no,
submit category 5
no,
or
not
will
not
be
not
definitely
so.
be able.
Okay.
No, you go ahead.
Yeah, so there were um the stitching screws. I think it was maybe 6-inch centers. I think the
Okay.
stitching screws
I,
were at 6-inch centers. So just 75 was just where they were, just to reinforce them. That's just to
okay,
reinforce.
understood.
Yeah.
Understood. Do you think that the claddings that we use are too thin? That the gauge of the cladding that we use is too thin? Number one. I will let you answer that. And the second question I had for you is it a logical conclusion, a logical assumption to conclude that after an event, because as engineers, we are taught that once material failure starts, that the material can no longer guarantee to withstand future events. So is it a logical conclusion to assume that after a catastrophic event, once you have been able to get through that event with the existing materials, because of the stress exerted on those materials during the event, that we should really change the materials after the event so that it can the new materials and the same method of construction. I'm speaking primarily to the roof, would be able to withstand future events because I'm assuming that the stress that it will be under, the tensile strength stresses and everything else will be under during the event from the dynamic loading will weaken the materials. So is it a logical
Yes.
conclusion that this should be changed?
Right. So first question then. We should be using 24 gauge cladding, 0.61 millimeters thick, for the metal. Right. So it'll be a bit thicker once you include all the paint and everything else, but the metal thickness, 24 gauge, that is in the OACS building code. So we shouldn't be using anything less than that. Sorry, well, anything thinner than that. So we do import, I guess, 26 gauge and maybe even thinner, but that should be used as maybe hoarding or something else, but not for houses, not for the structure of the roof. Regarding the stresses that materials go under, the recommendation really is after you have a hurricane, then take a look at the roof and see if any of the screws got pulled out. If they did get pulled out, then or nails, but it really should be if they're nails, then replace them with screws. If they're screws, then you should replace them with longer screws because the timber has already been weakened in that area. And if you can't, replace them with longer screws because maybe they're using some small purlins and the screw was long enough to begin with, and therefore it went through the entire purlin depth, maybe 2 inches. Then, yeah, you put those back in, but then put others in between those because those fixings have already failed. The screws are okay, but the timber has failed, so you can't use back that hole. You have to use a hole nearby. Just fix it nearby. That's it. But I think the
Now,
metal, you have to examine the metal if it is reamed out. Let me see if I can show this. Let me share this again. Yeah, so clearly that you can reuse it, but not right there. You have to put the hole here. So you can still reuse the cladding, but you put it here. That one, uh, you examine it, and if it is not damaged too much, you can use it. Obviously, those tearings you can't use, but you look at the reaming, and if it's reamed badly, then just don't use that area of it, right? So put the hole here, then put it nearby, and seal that. We can screw it in, then cover it with silicone, or put silicone in there, and then screw it in. But you know that's not going to be the one that's going to be used is this one here. Yeah, that's it.
Peter, any follow-up?
yeah, I was just wondering what is your estimation of the impact of the flexure of the cladding? Because the cladding itself will also flex based on what you were proposing it with regards to the wind loading, the dynamic wind loads. Would you consider the cladding to still be structurally strong to support future events?
Uh, yes, because I did the check based on, all right, if this is the interior, according to the code, from here to here, that's 1 foot centers, 300 millimeters. That's what's needed according to the code. Because of the fluttering, you then put one in the middle here. There shouldn't be much fluttering from this, right? That's the only thing left right here. But there shouldn't be much if you're fixing it here and here in the interior. Now, if it was fixed like this at the high pressure end zones, then you're going to have problems. And that's why this is what you do to prevent that fluttering here. So this is not going to work at the end zones. This will, or this should, I should say.
Okay,
Grenville,
thank you.
can you show that drawing you had of the end zones just to refresh people's mind of what you're referring to? And the next person up to ask
Yes,
question, yeah, go ahead.
right. These are the end zones here. So for a gable-shaped roof, the hatched area attracts more wind pressure than the interior, but these are the real danger areas. These black areas, the gable eave, the gable and the eave where they intersect, gable eave, or the gable where it intersects with the ridge, the gable ridge. Those are very high pressure zones. So you definitely need 3 inches there.
All right. Next person up will be Dominic Holder and then followed by Andrew Hutchinson. Dominic?
Hi, Grenville.
Yes,
Um,
sir.
Thanks very much for that talk. It was very,
Yeah.
very interesting and informative. I hope that you have better luck with the ice shakti in the future. I cannot believe that you said that that was their position, or at least they tried to get you to come together with the other society, and that's most unfortunate. Anyway, um,
Let me just interject though. No, that's the better method. The better method is if you have two persons given a technical opinion on the same subject, then the better route would be for them to get together and discuss the matter in sort of an evidence-based discussion. And that's what I try to do, evidence-based discussion. But the other side wasn't willing to. And therefore, the instructee did the reasonable thing, which was fine. If you cannot agree, then write two final papers on the matter, and that will be that.
mm,
Um, but yeah, I may go back to them now with the doctoral evidence, and maybe we come up with some better guidance then for all engineers.
yeah, I think that would be most useful.
Yes.
My question to you is my takeaway from this is that you're coming with like a twofold thing. So one, yes, you presented an argument for confined masonry versus reinforced masonry. The second is in terms of what wind speeds we should be designing to, hence the argument about the category five. Because I think if you weren't making the argument for category five and just for argument's sake, you're making an argument for category one, then I think comparing the two methods is probably less relevant. But at category five, it becomes extremely relevant. So I know you said you were working on coming up with a kind of overall region code, which makes sense to me. Because right now I find we've got lots of references. We've got cubic, we've got ASCE. In Barbados, we have debate kind of wind guidance. We've got similar differences with respect to seismic guidance in terms of applied loads. Forget about the actual system type. So is it that you are trying to tackle both things so that we have a wind speed directive in addition to a form of construction directive for the region that everybody, all the islands can kind of reference, basically?
Yes. So fortunately, that work has been completed. There is a regional code of practice for houses all over the Caribbean. One
Okay.
single, so no matter where you go in the Caribbean, if you follow that, now that was done before though, because I had done a similar thing for the Caribbean Emergency Management Agency, SEDEMA. They were trying to harmonize all the codes in the region, and therefore we just looked for the most onerous, and we came up with that. This one is different. This one is we are going right to category five to what we expect. Um, so that's why that is there now. So no matter where you go, from Haiti all the way down
Okay.
to Suriname, it's
So
relevant. However,
this guidance
yeah,
is available as we speak, basically.
yes. So it went through CrossQ. They had their technical committee look at it. I was the principal author of it. So we had people from around the region looking at it. And then it passed through CrossQ. And once it goes past CrossQ, it can go then to COTED. That's the CARICOM ministers for trade, I think economic development. Um, and they approved it in 2023. And therefore it became a CARICOM standard. So we do have this CARICOM standard that exists. So if you're doing houses, and it's very prescriptive, so it contains all the research that I did went into that. So all those details are in there for masonry houses and timber frame houses. Now for Trinidad, the highest then was category two for Trinidad and Guyana and Suriname because they don't really have that great hurricanes. But for everything north of Trinidad, it's category five.
Okay. What's the name of that guide?
Right, it's called the Learner's Guide.
Okay.
right? So it's free. You can download it for free. It's freely available, and it's a user-friendly version of the code. So the code is written, as in code language, but then we did a user-friendly guide for homeowners and contractors and everyone else, so that the homeowner can then read it and have the same knowledge that a contractor would have or should have. They won't have the contractor's experience, but they'll have the knowledge. So it's written very user friendly so that lay people can understand. And I keep telling that one I could upgrade at will almost. So every time we share it, we tell persons, actually, yeah. So if you look, there's a link to it in the chat. So I tell homeowners every time I do something, a seminar or something for homeowners or training, I tell them, just take a read of it. Spend a couple of days going over it, and anything you don't understand, if you find there's too much jargon or you didn't understand something, let me know so that we can upgrade that. Because that one doesn't have to go through Quoted. That one goes through Sedima. They have full control over that.
Okay.
It's easier to update that one. And the earthquake, similar thing. The earthquake really was for the worst earthquake we can imagine in the region based on the soils and the spectral accelerations. And that just happened to be Haiti.
Okay.
Thank you, Dominic, for your question. Engineering Fellow Hutchinson.
Good afternoon, Vincent, and Grenville.
Yes.
Grenville, let me congratulate you on an excellent presentation. You really been burning the night oil behind the scenes doing the research, and that's very good, very good.
Yeah.
I appreciate the presentation a lot. I just offer a few comments. Probably my first engineering observation I made when I was 6 years old, and the house that's in Hurricane Janet, and the house next door to our house at East Point, all the sheeting was stripped, but all the nails were visible. I subsequently learned that they were using aluminum sheeting, which is very soft.
Yeah.
But because of the sea air and the high corrosion, they thought it was wise to use aluminum sheeting and so forth. And they didn't use the nails with the big heads, So the hurricane just ripped off all the sheeting and left the nails standing. So I observed that when I was 6 years old. So that's one of my lasting memories of Hurricane Janet. I think one of the challenges, you talk about reinforced masonry and confined masonry. I want to submit that the reason they probably prefer confined masonry in Haiti is probably because the quality of construction blocks is so poor that you could build the blocks, but then build a frame around it and still make it strong enough. And that is part of a cultural practice. Well, there are many cultural practices throughout the Caribbean where quality does not matter. What matters is price. So you build something cheap because the people will buy it. That's what they want. So I don't know if you looked into the quality control of concrete blocks in Haiti, but I have a suspicion that if you're going to use poor quality blocks, then it might justify using confined masonry because the column, the reinforced concrete framing will secure it, and that might be the logic. I don't know. I just thinking aloud. But reinforced masonry is great, but I have to confess, as an engineer of 50 years practice, that has always concerned me about the quality control of filling the cavities with the rebar. That an engineer cannot afford to be on site every day. So he has to leave it up to the supervision of the foreman and the and the goodwill of the masons. But I have had cause to cut into a few of them to do inspections and found that it was not what I thought it would be. In other words, the cavities were not properly filled with concrete. And that really, to some extent, defeats the purpose or weakens the whole concept of using reinforced masonry. Just a few observations on my part. One last thought. I would wish if Barbados is flattened, not if, when Barbados is flattened by a hurricane, Cat 5, we then have a brilliant opportunity to rebuild to a higher standard. Okay? But until such time, the advent of codes and so forth will have a limited impact on what exists at present. However, I therefore think that engineers should focus on explaining to homeowners how to create a safe room within your house. Now, in other words, the average homeowner probably is going to say, man, I can't do all them things and I'll reinforce all them roofs and things, and that's too much money. But it is possible they could be advised how to take one room and make it a safe room so that in the height of a hurricane, they can go there and sit safely and let it pass. And I think engineers are remiss in not pushing that concept, because it's a lot more achievable in the current situation than saying to everybody, this is the building code, this is what you got to do, go and change up your buildings to retrofit. It's not likely to happen. There are my thoughts.
Yes. Yeah, they're very good thoughts as well. I will address the second one because you're right with well, let me just address the first one because the minimum sheeting that you should be using in aluminum is 0.7 millimeters, but again, that probably was not available back then. That was a long time ago.
No, yeah.
Yes, so you just have to get what you can get. Regarding the weakness of reinforced masonry, you're correct, absolutely correct. The weakness is that the fellows simply do not grout the cores properly. Even though the code is clear, the building codes, even our old codes, is every 3 courses you grout. 3 courses grout. And I stress that when I'm on the site. Every 3 courses grout. And it's rare that you would have seen that. Usually the fellows just build all the way to the ring beam and then try to force the stiff concrete that they're pouring the ring beam into the cores, and it gets clogged up near the top. And therefore, when I go and visit, I can guarantee that cores are not filled and you have rebar and they're corroding away. Most houses, I would say, the vast majority of them, over 95%, are basically unreinforced masonry. Because though there's a rebar there's not the grout there. So therefore, they're effectively reinforced masonry. But if you could just keep pushing, even as engineers going on the site, telling the contractor and even the masons, every 3 courses grow, every 3 courses, not 4, not 5, 3. Then you try and maybe push that. Because I don't know how we lost. I really don't know how it is that we lost all this knowledge. But again, we are no longer doing the apprenticeship system. So people, they go to wherever they go and whatever they learn, they don't learn these fundamentals. Or maybe they do learn them, but then they come onto the site and they're trying to push what they learned. And then the senior people on the site say, well, let's stop with that foolishness. We are going all the way up. And therefore they don't have any influence. But and also, unfortunately, yeah, go ahead.
Also, quite a bit of block work is built on a piecemeal basis, a unit price, so much a block. So they're in a mad rush to build a lot of blocks in a day to get a good price. So they may neglect the quality of grouting.
Yes, which is why we have to go, I believe, to the homeowner. We try to explain to the homeowner how simple it is. That's why we have the learner's guide, so that the homeowner who is the largest stakeholder, they have an interest in having a durable and strong house. Hopefully they will look and see the pictures or the diagrams in the learner's guide. They look on the site of what the contractor is doing and say, look, you're not doing it this way. Which is why my recommendation usually is, because in Barbados, we tell the contractor for houses, well, just build the approved town planning drawings, and the approved town planning drawings have no rebar in them whatsoever. Then they should build the town planning drawings in accordance to the standard in the learner's guide, which is then the Category 5 hurricanes and the earthquake to Haiti. And the last thing about that safe room, that is wonderful. And and I'm pushing as well because I just finished a housing recovery plan for Grenada and Carriacou and Martinique, and that was one of the recommendations. Because if you can't afford to do the whole house, then at least do a room. At least do a room so that you're not homeless after the next hurricane.
Correct.
You don't want to be homeless. Being homeless is miserable. You prefer to at least have your goods in one place. And if you fix one room, then you go when funds are available to go and strengthen another.
I think we as engineers should lobby that point more, because it is a valuable point that you can't. Very few people can probably afford to retrofit the house to Cat 5.
Yes.
But you can probably afford to provide construct a safe room.
Yes.
Okay, thank you, Engineer Hutchinson. Grenville, we do have some questions for you in the chat, and I will address them to you in turn.
Okay.
First question comes from Carl Cadogan, and he's asked, any results or observations for standing seam on hip roof and their failures or successes at Category 5? So that's the question to you, Grenville.
Yes, I didn't look at that. I just looked at the trapezoidal and the sinusoidal type. But I would say just follow the recommended method, which is design it, because again, we do have the stresses for these materials, and therefore we can design the sheeting. We can design all parts of the house. Normally, sometimes persons, they design the structure, the main structure, and then they leave the cladding for BRC and whatever they will recommend. But no, we should be specifying what that should be, which is basically 6 inches all over. That's the spacing of the sheet of the fixings, and 3 inches in the vulnerable ridge, valleys, eaves, gable ends.
Okay.
And then once you've designed it, again, look for areas where you will get fluttering, and you will get fluttering in between the fixings, which is why you use those kind of fixings. So I understand standing seams, right? That's a little different. Again, design it the same way, but then look for where you can get movement and try to reduce that movement. That's just the basic philosophy of it. Reduce movement, because once movement is there, you will eventually get failure. So try to stop the movement.
All right, thank you for that, Grenville. Second question comes from Engineer Palmer, and he's saying, good evening, Engineer Phillips. Did you carry out any wind tunnel testing on your proposed stitching arrangement for roof cladding?
No. What I did is I calculated the stitching arrangement in accordance with the codes. And then once I had that, then I followed my best advice, which is look for movement. And then I realized that's where the movement was, and therefore I fixed the thing there. So the information from the wind tunnel testing is already in AC7. So they've already done that, because there are 3 ways. There are 3 ways of doing this research, sort of, or determining what recommendations you make for Category 5 hurricanes. One, you do a mathematical model. So you do a mathematical model and then apply the loads mathematically and see how it is. Just follow the code. 2, you do a physical model and send it through a wind tunnel or put it on a shaking table, apply your strain gauges to it, and then determine what the measurements are, and you come up with your loads that way and the behavior of the material and your recommendations. Or 3, examine the damage from an actual hurricane event, because the other two methods are simplifications of the complex series of combinations of variables in the real world. And because it is so complex, what we tend to do is simplify it with our models. Whether it is a mathematical model or a physical model, we simplify the complex behavior of what happens in the field. So I chose the third method, which is just look at the damage. And I can tell you that the university sort of slow walked it, seeing my application, and nothing was happening. And then in 2017, I asked the university, can you give me sort of formal approval to start early to take advantage of the 2017 hurricane season? Because they'd asked, well, I want to do this third method, but have I ever seen any damage from a Category 5 hurricane? And I said no, because I hadn't. And well, that's why it seems like the slow application. But in 2017, there was Hurricane Irma that devastated Anguilla. And I was the lead on that team to do hurricane assessments. And did that. And then when I finished writing the report with the rest of the team, suddenly we had Hurricane Maria in Dominica. And I requested to be on that team too. So I then got all the data that I needed. And then my application was formally approved, and that's the end of that. But when I finished writing my thesis and I was getting ready to hand it in, then in 2022, we had Dorian. No, sorry, 2019. 2019, we had Dorian. And that was like a hurricane, like a 3 days over a country. That was a game changer. Not so much in terms of the speed, because we had that before in Irma and Maria, but it was just staying there for such a long length of time, so that anything that was moving would come apart. And I had to rewrite the thesis addressing that movement. Hence, that's the result of it.
Thank you, Grenville. Grenville, a couple questions from me. The guides and so on that have been produced primarily focus, I assume, and you can correct me if I'm wrong here, to new house owners, persons now starting construction, etc. Is there an opportunity in the future to do a guide for retrofitting? To Andrew's point, we have a well-established housing stock in Barbados. And I think as professionals here, we are all aware the level of devastation that potentially will unfold here in Barbados, given that we don't have any mountains and valleys to the extent of some of our neighbors. So the level of devastation that could occur here could be extreme. Is there any room for producing a guide for retrofitting of homes?
Yes, so that was also done. There was a project that I did for the Ministry of Housing, because they said, fine, you have this for new houses. What about the existing houses? And I was asked to then do a guide for existing houses, timber walled and concrete block and coral stone masonry. This is the timber houses, the buildings that we have in Barbados. And that's done. And it's with the ministry. And it really should be released as a public document. When I do work in other countries, I let them know about it, and I ask them, please write to the ministry, write to the PS from the secretary, and ask them if you can use it to upgrade your buildings, because I can't release it because I don't release clients' work. It's just
Grenville,
unethical.
could I ask then that you furnish the association with some information that we can write formally
Yes,
to nudge
right.
the ministry?
Yes, right from the secretary and the Ministry of Housing. It's the same guidance I give everyone else. Right, the permanent secretary in the Ministry of Housing. and ask them, please, can this be released as a public document?
Okay.
I have no problem with it, and please release it. People need to benefit from it. Also, it's version 1. I specifically put on the outside of it version 1 because the hope is that as it's released into the engineering community, people see, all right, what about this and what about that or this, whatever it is. Is an easier way to reinforce unreinforced masonry blocks because I have a method there, but then people may find the easier way. Good, let's update it, and therefore we have version 2, version 3, whatever. But at least the version is there. I guess the better thing perhaps would be having it online as a resource, and therefore, as it's updated, then the current version is always online.
Yeah, thank you for that, Grenville. So I have a question from some family I did not know I had, Mr. Harold Jones. So Harold, over to you, sir.
Grenville, this is Harold.
Yes.
This is Harold from New York.
Yes.
As you know, my background is nuclear engineering, but I have a question, and I'm actually working on a study with some universities because since Sandy here in my neighborhood, 10 years, 11 years later, we see sinking of homes and stuff like that after that. So we have a consortium of engineers that we're working on this. But my question for you is in Barbados. My home Barbados was built in the 60s, my dad. And they have these what you call decorated blocks with in the top of under the roof or whatever that. I look at it when they come in. What was was these masons? I know it was built by a mason. It wasn't built by an engineer, but was those blocks where the wind can come in? Was that to help the roof, or what was the reason for having this construction? Now my kids want to stop them up and put air conditioning, but what was the reason for that, if you remember?
Yeah, but I can guess at it. I'm sure there are engineers here that are a lot older than me who may also have an opinion on it. So everyone is welcome to share. But before the codes, which came in around the 70s, the early 70s, Irwin codes, and then they got updated in the 80s, and then they keep getting updated. Not so much in the Caribbean, but ACE7 and others. The American codes, the British codes, they get updated, and we adopt those. It seems to be they learn things by trial and error. So they recognize that there's a lot of pressure building up under the roof, and therefore to relieve that pressure, you have these blocks that can allow air to pass through them. Now, whether that worked or not, I'm not sure. Right? So others are welcome to chip in to find out, because that may be the reason, and maybe they did it because they found that worked. But whether it worked or not, I don't know. I was not around during, it was not even a thought during Janet to examine houses that had those and whether they survived or not.
Andrew,
I'm not
would you
sure if
like
there's
to offer comment here?
Yeah.
Yeah,
sure
I think
if
I'm
there was a
not.
study done after that. I'm not sure. I haven't seen it.
It's a good question. I'm not sure where Mr. Jones, these blocks are in the gable end walls, or these blocks are at high level,
High level, all through the house,
but above the ceiling or below the ceiling level?
below the ceiling,
Okay.
like in the bedrooms and all the
Yeah, well, it would have been for ventilation, but Grenville is right. There's I think, a misconceived theory that if you're going to get a buildup of pressure within your seating space, that you can, if you put enough ventilation, as I say, it will come in and go out and balance the pressure. But I don't think I don't support that theory. I think that is a wild guess, really. Not sure what's going to happen. But I've seen quite a few houses of that era built with grill blocks, ventilation blocks.
Yes.
in the eaves, in the gable, sorry. And that's primarily to allow ventilation. So you get, because instead you get a buildup of hot air, the hot air can escape. But at high level, above the windows, below the ceiling, that would have to be just for ventilation.
It is good ventilation, but my point is, I'm skeptical about stopping them up because, but the kids need air conditioning and they really want to get rid of them. I feel it worked because the roofs came off and that nothing happened ever to my roof. So I don't know. I think.
Well, what you can do, you don't have to stop them up. Just get some concrete board and put them in front of them. And therefore you can use the air conditioning. And then if they move out and you can then remove that concrete board and get your ventilation naturally again. But what I would recommend, again, my purpose here is twofold. One, to demonstrate the research that I did, but also to encourage as many of you as possible to also pursue doctoral studies. You can do it now. Before, I guess you had to spend all the time doing a PhD, a Doctor of Philosophy. But you don't have to do a Doctor of Philosophy. You could do a Doctor of Engineering. You could do a Doctor of your profession. Just like uh, medical doctors, they do a Doctor of Medicine. They already have their doctor degree, like
MD.
Doctor. Yeah, they have the MD. They call doctors, but they then go and they don't normally do PhDs. Well, I guess some do if they're doing a lot of research. But those who are practicing, what is allowed now is that you could become a doctor of your profession. So a doctor of engineering, a doctor of business management, a doctor of medicine, a doctor of your profession. And that's the way for practitioners. Now, if you want to go into full academia, then I suppose you go and do the the PhD, Doctor of Philosophy.
Grenville, before we
Yes,
close, I am aware of time. I want to get in these last two questions that are in the chat, if you don't mind. The first
yes.
question is from Belvin Thorpe. He says, "Good night, Dr. Phillips. My simple question is, are there any Caribbean countries that have their building codes mandatory?"
I think Grenada has a law where they have adopted the 2015 OECS building code, and that is the law. Um, so I think it's mandatory there. So yes, I think so. Nevertheless, Hurricane Beryl came and there was damage. There
Okay.
needs to be auditing of planning departments to just check to see what they approved and then improve the planning authorities around the region
I think,
because they're the gatekeepers. They're the gatekeepers.
Vincent, I could add to that. Just on my experience, I've done projects and submitted to planning in St. Lucia, St. Vincent, Grenada, most of the islands. And yes, Grenada, they definitely, when I submitted there, the planning department requires to submit, full construction drawings, RC drawings, etc., in compliance with the code. And also St. Lucia. St. Lucia, but they're the only two that I know that kind of, rigidly enforce it.
I see
Um,
Justin Leslie has mentioned that Anguilla now also has a mandatory code. I guess that's coming out of our UK influence, but I guess they have as well.
yeah.
All right, thank you for that. The next, our final question for today to you, Grenville. Good day. I am a civil engineer and lecturer at UTech Jamaica. Sorry to have just joined. I missed some things, but my question is, this document that you speak of, Grenville, that deals with retrofitting, is there consideration to have the content included in building codes?
Right. That's a very good question. Yeah, possibly what we could do is when we when we upgrade the learner's guide, we can have a section there dealing with upgrades. Maybe that's the best way. And I'll just do things from scratch and do it there. Or talk to the Ministry of Housing there and let them know what we're planning to do for the sake of the region. So I would, yeah, so we can have both efforts then. You could, yeah, as bait, you could write requesting that it be released, as a Barbadian document. And regionally, we can see what we can do about including it in the upgrade to the learner's guide.
Okay.
Yes, that's brilliant. Yeah, this light just came on. Sorry.
Thank you, Grenville. I want
Yes.
to thank you, Grenville, for, like I said, a very informative discussion this evening. Very technical, but very informative and very useful, I think, for those persons of a civil structural bent, especially that would have joined the meeting this evening, and those with a general interest in engineering. I mean, seismic activity and hurricanes are something that affect all of us, regardless of the part of the profession that we practice. And certainly, if we are impacted, regardless of where we are, it affects everybody at some level. So I think these are things that we need to discuss more at the regional level and certainly find those synergies and bring pressure to bear where we need to bring pressure to bear and bend the ear of authority figures so that we can get more information into the public sphere and perhaps start to make things happen at the construction level. In a region where we have very poor regulation in terms of inspectors and so on going out to check housing at various stages, I think we need to do certainly better in terms of quality control to ensure that at least at minimum what is required in the information that you mentioned is being done, which could eventually save lives. You have a follow-up comment, sir.
Yes, I can send you the presentation if you want. You could put it on the
Yes.
website so that anyone present or those who didn't attend, they could take a look at it.
Yes. What we will do is we will have this recording available on our website in the coming week. But
Yes.
by all means, Grenville, if you could share the actual slides for the presentation, that would also be
Yes.
useful. Because as I said, this is extremely important and useful information that was shared and the interactions that was shared here this evening. So thank you so much, Grenville, for affording us your time. I want to inform members and our regional colleagues who are here that coming in the new year, perhaps we'll visit again with Grenville to explore that doctoral mind to see what else we can discuss. I also want to inform members that coming up in the near future, it's still being worked on. We will have a presentation being done by Engineer Fellow Andrew Hutchinson, which will be speaking pertaining to rainwater, flood mitigation, etc. We're still working out those details, so keep an eye and an ear out for that presentation. We haven't determined if it's going to be an in-person or an online session. If it is in person, we will record it so that we can share with our colleagues overseas, and we'll see how best we can stream that if it is in person. But I want to thank you, Grenville, for sharing of your vast knowledge and experience with us this evening. And certainly, we look forward to digging into that mine a bit more and to learn more of your experiences, having been around the region for the last 20 years, doing risk mitigation, inspections, post-disaster inspections, etc. Perhaps something more that some of our professionals need to consider, and certainly for our students who are here, that to give them an opportunity or an ideal of areas within the profession that perhaps they might not have even considered before. So thank you, Engineer Grenville, and I do wish you well for the remainder of the year. Just some reminders before we complete our session this evening. The Barbados Association of Professional Engineers, we do have our social or our line this Friday, December 5th, 2025. That is being held at the LV Harcourt Lewis Training Center, Barbados Public Workers Cooperative Credit Union headquarters, which is located at the Keithbourne Complex in Belmont, St. Michael. Our start time will be 5:30, and we will be running until 9:30. All are invited. I want to remind members that 2026 is literally around the corner, and January means your yearly memberships are due. Corporate membership, $300. Affiliate membership, $225. Graduate membership, $150. Student membership, $20. For those who are professionals and need to do their registration, that fee will be $1,250, and that is to be paid to the registry at the Supreme Court before the end of January. I want to thank you all for joining us and for supporting our events and webinars for 2025. This will be our last webinar for this year, but we certainly do look forward to you joining us in 2026 as we explore other technical topics pertaining to engineering or topics that affect engineers or that engineers have some influence on. I would like to wish all of you a very Merry Christmas for those of you who do celebrate the Christmas time, and certainly a happy, prosperous, and successful 2026. Thank you and good night.